theoretical, but it does not give the full picture, since the runtime behavior also depends on dynamic effects, for instance variations in timing and interference between tasks or threads. Such dynamic effects are emergent properties that are not visible in the source code. To get the full picture, you also need runtime monitoring. There are at least 3 types of runtime monitoring. The most common one is probably application logging, where printf debugging is a prime example. This is very flexible, just insert some print statements and you get a textual log of your application. However, this is often associated with a considerable overhead. Outputting a string of, say, 15 characters over a UART at 115 kilobaud takes about 1 millisecond, which is unacceptably slow in many situations. Moreover, it's often not appreciated to have printf lines all over the code. On the other end of the scale we have instruction trace, where the data is not generated by software but by the processor core. This means essentially zero overhead, but the scope is limited by the hardware implementation. For instance, it's often not possible to record function parameters, return values, or local variables. This also requires expensive bulky equipment, and you need a processor and a board that supports high-speed trace ports. Moreover, this produces a very large amount of data on low abstraction level that can be difficult to overview and analyze. A middle path is software event tracing. This has the flexibility of application logging, but is much faster, measured in microseconds per event. Moreover, the instrumentation is typically predefined within the RTOS or middleware APIs, so you don't have to insert a lot of printf statements in your code. At Percepio, we currently focus on software event tracing and application logging. Percepio provides visual trace diagnostics, which is not just a tool for runtime monitoring, but a solution for efficiently gaining actionable insights throughout the development process. We combine efficient solutions for runtime monitoring with advanced data processing that actually understands the meaning of the events and builds an OS-aware model of the recorded data. This is made accessible and really nice to use via bespoke data visualization with over 30 interactive views from different perspectives and at different abstraction levels. Tracealyzer is our analysis and visualization tool for trace data. It also provides live real-time recording capability for FreeRTOS, SafeRTOS and MicroC OS 3. It also supports other real-time kernels and operating systems via third-party tracers. It is ideal for system-level debugging and works a bit like a surveillance camera for your embedded software, where you can identify issues in high-level overviews and then zoom in to see specific events in detail to understand the cause of the problem. DevAlert is our new service for IoT devices that allows for direct feedback from customer operation or from field testing regarding runtime errors and other software events of interest. As you know, software is rarely bug-free even at release, and the sooner you can become aware of missed bugs and fix them, perhaps via an over-the-air update, the fewer customers will be affected. If you react and deploy a correction fast enough, most of your customers probably won't be affected or even notice the bug in the first place. DevAlert is a cloud service that provides a DevOps-style feedback loop from the devices back to the developers, and also provides traces for remote diagnostics in Tracealyzer. We provide a reference implementation for AWS, but other cloud vendors can also be supported. You find more information about DevAlert at https://percepio.com/devalert.
Thanks very much for the product overview of Tracealyzer, Johan. Let's move on to the Storyboard demo side of things now. So first I'll give you a quick overview of the demo we're going to show you. This is going to be based on the IMX RT1060. This is the EVK board, and if I quickly show you the demo application, I'll load this up in a moment inside of Storyboard and show you how it runs. But essentially it's based on a white goods demo for a washing machine, and we're using the hardware on the EVK board. So if you've not seen this, it's a 480 by 272 LCD panel with a capacitive touchscreen. And in our demo, we'll be configuring Storyboard to run on the FreeRTOS OS with the MCU Espresso IDE runtime. We're also using PXP animation-based hardware acceleration, and we'll be using a virtual file system. So this is Storyboard deployed not in file form, but in a header file form for incorporation and build into your application. So this is using our C or C++ resource header format. So if I show the application now, this is Storyboard desktop. This is the screens, the raw screens that we have. You can see we've got a number of screens. We've got some animation here, and this first screen, when I show you it running, is using a touch interface, and this allows you to scroll up and down and interact with the display. So this will be running here in our simulator, and if I show you the kind of activity, this is a touch. If this was a touch screen, I would be scrolling up and down, and we can hit start, and it's simulating a wash machine application. Okay, so that's what we're going to run on our target. It's pretty good. We've got this set up to run pretty smoothly, and well, we'll hopefully show you that next. So we're running on the board. What we've done is we've used a configuration called the LPC Link 2 configuration. This allows you to set up the board in a special mode, which gives you a much faster flashing, and also crucially some additional trace options. So we're going to be using the SWO, the single wire output trace, for real-time trace output while we're debugging the application. You can see here there's an application note on our website, and also there's a couple of little jumpers and things that you have to change to the board. Of note here is that you need to power this using the external power configuration, which is what we're showing here. So normally you can run the board with just a USB connection, but in this case you need to configure to the external power, which I've got here. So back in the application, this is Storyboard Designer Desktop again. What we'll show you is how we've configured this for export. So we'll be using a virtual file system on our target. So I'll be choosing the virtual file system, and I've actually prepared a configuration here which allows us to tune the application for flash versus memory. What you can see here is we've got lots of images, and we're going to be looking at 9 megabytes. This is for the animation. We're using a flip chart animation. So the spinning drum you saw is using lots of background images you can see here. So we're going to queue those up, and we're also going to store them in a compressed file format. So we'll be using not as much flash, but a reasonable amount of the SD-ROM. Okay, so using that configuration, we can export the C++ header file. We're going to be generating a model file, SB Engine model.h, with the embedded resources in, and I'll run that. It takes a little time to do. So what I've also done is prepared one here. So in this export file, we'll have a binary representation in a C++ header format of the images, the resources, and everything else. So we'll be using that in our application, and we're going to be building it in as part of the source code. So now let's take a look at the source code side of things. So I'll switch over here to my MCU Espresso IDE, and what I've done is I've loaded up an application which is based on one of the two sample apps, the Coffee app and the Hello app, which we include in the NXP SDK for the platform IMXRT 1060 and 1050. So that's included in the SDK download as middleware. You can download that and try it yourself. So what I have is I've modified this to add a couple of extra tasks. So we've got Storyboard Engine main task. This is the GUI task. We've also got an additional task for input. This is going to be polling the touchscreen. And a couple more tasks, hello and loading, are meant to simulate additional features and behaviors on the board. So this is maybe a state machine or some other UI control. Loading task here is simply blinking an LED and doing some GPIO. So if I switch over to the Storyboard task, this is going to be running. What I've done is I've enabled some logging here. So this is Storyboard internal logging. So we use this to help diagnose issues and to look at performance behaviors on a target. This allows us really to look from the inside of Storyboard outwards, and this gives us a really good insight into the kind of information that's going on. And helps us to highlight performance issues. Now, what this application is currently configured to is to show kind of some loaded behavior, some behavior that's not ideal. So if I switch over to so you can show the board webcam, I'll hit run there. First thing you see is it takes a little bit of time to start up. So that's loading up there, and if I zoom in a little, when I'm moving the screen up and down with touch, it's a bit laggy. You can see there's a kind of a notchy behavior on the lag behind the touch input there, and it's kind of hard to see, but the animation's not as smooth as it could be. Okay, so what I can do now is make use, if I pause that and reset. Okay, restart again. What I can do is make use of our SWO output here. So the Storyboard trace that I enabled is now piped directly to the output of the board, the debugger back channel, the SWO output. And that allows us to capture a whole load of trace information from Storyboard as we're running. So if I run this again, you can see here we're outputting a whole load of internal trace data coming out of the trace port here. That's the initial startup, and we're going to be doing some scrolling there, and let's do the animation again. Okay, cancel that and reset, and let's stop it there. Okay, so all of this information from boot up is now collected in my trace output. I can save that to a file. This is going to be a plog file. Okay. And this is the kind of file that that Storyboard is able to load. So if I switch back to Storyboard, these files are saved in plog form, and you're able to poll them to kind of load and deconstruct them inside of Storyboard. And this is our own internal trace information. So you can see here that that we've got some screens being shown. You can see the average redraw times, and this kind of detailed information is very good at analyzing Storyboard behaviors, but it doesn't really tell us much about the outside world, so the external influences on Storyboard which are affecting its behavior. So you can see here we've got some additional tracing for graphs and redraw times, and that allows our engineers to capture this trace and in our customers. And this is our own internal trace information. So you can see here the diagnostics, and I can drill now into the home screen and some timer feedback. So this is all of the activities inside of Storyboard. You can see here inside of the washing screen, this is where we had the animation run. You can see each time we redraw the screen, we're looking at at drawing a new image. So it's kind of a flipbook animation. So this is really very useful information to allow you to diagnose things. But as I said before, it's not necessarily the full story. So this is where Percepio comes in, really. So what I've done is I've added some additional trace capability. So Percepio provide a bunch of code here which you can integrate into your application. In this case, we're using the snapshot mode. So what I can do is now I'm on a halted breakpoint. I can pull back a whole bunch of different captures. So let me just do that now. I'll reset to the beginning, so we've got a clean state. And what I can do is I'll go into our application task here and set a breakpoint on the first screen that's shown. So here, this is display init is when we're setting up the application, and here display update is called every time we've got something to display. You'll see here that I've included a few extra trace outputs. So this is going to allow us to to basically add some detail to the Percepio trace. So if I hit that again, I'm going to run that. We'll see the same startup. It's going to load up the application, and then I'm hitting the breakpoint. Okay, so if I had that so you can see it. What I can do now is hit the plugin from Percepio, which allows me to save a snapshot trace. So that's going to use our logging and tracing we've added with backtrace capability to pull back all of this information. This will be analyzed in a moment. So that's going to pull back a log file and extract the data straight out of the memory and load up inside of the Percepio Tracealyzer tool. As you can see it loading here. So what's interesting is, and I'll let the guys from Percepio talk a bit more detail about this. You can see here we've got a capture from startup. So now we've got a log file here. We are able to share that with Percepio team, and they'll do some debugging. So we've got our trace log captured now. That's ready to be shared. By way of handover, I'd like to just to recap what we're looking for here. So some of the startup time was not what I was expecting, so we're looking at optimizing startup. Some of the animation could be improved and general performance. I think there's areas where we can look at there in more detail, and also investigating why there was this apparent lagginess on the touchscreen interface, and that was visible in the menu. So let's hand over to Johan. I've shared this file already, and let's look in more detail using the Tracealyzer tool.
With Tracealyzer, we can get a broad picture of the behavior at system level. This is a general tool for visual trace diagnostics that can be useful in many types of embedded applications. This system runs an RTOS kernel that provides preemptive, priority-based multitasking. This is an efficient and convenient way to handle multiple tasks in parallel, such as waiting for touch input while updating animations on the screen and also responding to network messages, for instance. When using an RTOS, the tasks are essentially running as separate programs, ideally with one responsibility each. The RTOS kernel rapidly switches the executing task as needed and gives an illusion of parallel processing. Tracealyzer shows you exactly how the tasks are executed by the RTOS kernel, as seen here on the left side. Note that the timeline is vertical in this case. There is also a horizontal mode, but the vertical mode has certain advantages, as you will see soon. Each of these columns represents a task or an interrupt handler, and each of the solid rectangles are fragments of uninterrupted execution, separated by task switches. There are several tasks in this system, and it appears as this task, SB engine, which is currently initializing the HMI, only receives about a quarter of the processor time. The rest is mostly used up by this light green task, loading task. This becomes very clear in the CPU load graph, which has an horizontal orientation, as you can see. And by selecting the loading task here, we can also see that the average value is about 72% up here in the selection details. Note that the order of the task columns and even the task colors are assigned according to their scheduling priority. This makes it easy to see that the loading task, the light green one, runs on a higher scheduling priority than the SP engine task in dark green. Most RTOSes uses fixed priority scheduling. This means that higher priority tasks always gets to run until they suspend themselves or are preempted by an even higher priority task, while lower priority tasks, like SP engine in this case, has to wait for all higher priority tasks to finish. The benefit of this is complete control of the real-time behavior. The drawback is that the scheduling priorities become critical for the application behavior and performance, and it's up to the application developer to find suitable task priorities. This is perhaps easy in a toy example with 2 or 3 tasks, but can be quite complicated to get right in real applications. To see more details about what the application is doing, we can display user events, as we call them, that have been logged in the application. Note that the screen reads zoom in to show number of events here. Okay, so let's zoom in a bit. So here we can see a lot of details, like individual memory allocations, for instance. But we want a bit more overview at this point, so let's change the filter instead and zoom out a bit. Now we can overview the user events from the application, and we can see events like poll input start in this yellow task called Storyboard input. This seems to be related to the HMI touchscreen input, and we can measure the time between these task activations like this, and see that it's approximately 200 milliseconds in between them. So it appears that the touchscreen input is only sampled with about 5 Hz, and that could explain the laggy behavior. So it seems that the problems were that the loading task were running at a too high scheduling priority, and that the storyboard input task only executed every 200 milliseconds. This was just a basic example. There are a lot of other things we can see with Tracealyzer, especially overviews that makes it easier to spot issues also in long traces. For instance, in the lower right you see the memory allocation over time. Each of these data points corresponds to a malloc or free event, and by double-clicking it we can find it in the trace. In this case we should probably adjust this view to appear a bit better by removing the unit from the y-axis and by hiding the markers for the individual events like this. Another example is the communication flow graph. This shows how the tasks are interacting in runtime, and is essentially a dependency graph based on the trace data. We can click on this message queue, for instance, and see all operations performed on this object, like sending or receiving messages. This opens up the object history view, where you can double-click on the events to find them in the trace. In total, Tracealyzer provides over 30 different perspectives, and all works like this, interactive and interconnected with other views. This makes it easier to drill down from an anomaly spotted in a high-level overview down to the detailed events to see the cause. And with that, I hand over to Gary to continue. Thank you.
Well, thanks very much, Johan. That was really great. You can certainly see the power and the insight that Tracealyzer gives us when trying to analyze an application in the context of a wider solution. You can see the interaction between the tasks is very hard to visualize unless you can really see what's going on. So just to recap where we were looking, there was certainly work to be done on optimizing the boot and the general startup. We saw there's some scope for the improvements in the animation and general smoothness of the application, and also we saw that there's certainly something that we can do in terms of the touch response. So what I'll do is I'll switch you over to the application code and just show you the changes I've made. So the first item that was identified was the priority of the loading task. So in reality, this task is just a dummy task. It's actually taking up lots of the processor time. It's also cycling around just reading the GPIO pins and blinking the lights. So it's illustrative of a general task in a wider system. The key thing really here was that the priority was set quite high, and that was continually interrupting, as Johan mentioned, the storyboard, the SB engine task. So I've dropped that down by 1, so it's at the same level of priority as the storyboard engine tasks here. And the second area that was identified was in relation to the touchscreen interface. What I did here was looked at the polling interval. We had it set to 200 milliseconds as was shown in the trace. What I've done is drop that to something like 50 milliseconds. So this is going to be polling much faster and should give us a much tighter response without the visible lag that we're seeing. So if I switch over to the board here and show you that running. So I've just hit play, and we're going to see the initial startup there is something like 2 seconds. Previous it was around 5 seconds. And I think there's more we can do on this, by the way, and I'll come on to that in a second. You'll see next, if we look at the scrolling of the menu, much more responsive, much smoother. So here we've removed that visible lag and that notchiness by polling the touchscreen a little bit faster. And finally, if we pop over to the final screen here, we're looking at the rotating drum animation. This is a sequence of images queued up and played that we saw earlier. So let me show you what I did. I took the opportunity to capture another trace. And if I switch over to the Tracealyzer view here, what we found was first that you can see that the tasks have now been reordered, so the priorities are now in line, and you can see that the SP Engine task is sharing much more of the processor time with the loading task, so they're playing much tighter together, much more cooperative. And you see here the interval between the storyboard input task, the polling of the touchscreen has been reduced, and that's again gives us responsiveness. So one thing I wanted to call out was you may be wondering what the slope of the graph is here. So this is the memory utilization over time from startup. What this is actually doing, you'll see this ramp sequence here, is that is preloading all of the 30 or so full screen images that we're using for the animation on the rotating drum. So this is what we call a flip book animation, where we're queuing them all up and then flipping between them. To cause you the kind of visual rotation. So what we could do is actually defer that loading until later in the application. These two notches here are actually the initial and the second screen. You see, if we remove or defer this loading and pre-caching until later on, just in time for the animation screen, we'll be able to remove that whole 2 or so seconds of startup time that was taken up front and push it later on when we're not going to notice it in the application. So that's just one example of some further optimization we could do. So I hope that's really given you some valuable insights and how these two tools can be used together to create a fantastic user interface. Certainly thanks to Johan, and I think with that we'll conclude our demo and hand it back to the presentation. And just to recap before I do that, we're going to look. Basically, we've achieved our objectives. We've had a faster startup with much smoother animations and much smoother scrolling with the faster touch response. Okay, so I'll hand it.
Thanks, Gary. I'm going to pass things back to Megan, and we'll just kind of wrap things up.
Yes. Let me share our last key takeaway. Oops, wrong screen. Bear with me for a moment. And it appears I'm frozen here.
That's okay. I can take it from there while we're doing that. So just some of the key takeaways from today are definitely, if you're looking to utilize the 1060, the RT 1060 in your next embedded project, then definitely visit www.nxp.com. /IMXRT 1060, and you can order your own EVK kit so that we can kind of test out the graphical performance of it for your embedded project. Also, from Crank Software, we do have a 30-day free trial, so it's a full-featured free trial. So definitely give it a download today to basically get your hands on some of the demo images that we have already pre-built for the RT 1060. So that way, making it a lot easier to evaluate the graphical performance of it. And of course, the folks at Percepio also have a free eval version of the Tracealyzer, and you can get that from percepio.com as well. So with that being said, I think we're going to kind of open things up to the questions. So now is a good opportunity that if you do have any questions, get them in, and I'll pass things over to Megan.
Yeah, so let's get started. It looks like we have a couple of questions that have come in. It looks like this first one might be for Gary, but let's see. All panelists are welcome to address these. So the first question is, you used the SWO feature of the debugger in the demo. Can you explain how to set things up and why use this instead of a UART?
Sure, thank you. Yeah, it's actually a really cool feature. So it uses the onboard, the on-chip debug core, and it only uses a single pin. So you're not going to be taking lots of I/O from different application use cases. So what we do, we've actually I think I can share, or maybe if I post it into the view, one of the organizers can share a link. We've got a knowledge base article about going through this. You simply just enable the pin in the pin mux, switch on one of the features, one of the internal peripherals, and that allows you to basically talk directly out of this single Y pin with a printf style of statement, which is what we've hooked in our application. So it's really easy to do. It shouldn't take up any I/O resources, and it allows you really to turn this on and off in the background. So you're not really enabling or disabling or changing code. You can do this with just a single register. So yeah, it's pretty easy to do, and it's something that's which is enabled by the LPC Link 2 configuration of the RT1060 dev board. So hopefully that's answered your question.
Mm-hmm. Thanks, Gary. And it looks like there's another one here for you with regard to the capture trace buffer. So how big is the capture trace buffer and how much memory is being reserved?
Okay, that's a great question. So in the demo, I've kind of set it up to be quite large, to be honest. So we've configured it for about 400K. Now this was specifically so we could capture quite a lot of detail from startup, maybe 10 seconds or so, and it's more than you would normally use. So you can change this actually with a single header define, and I think it's all documented in the Percepio integration guide as well. So to answer your question, yes, about 400K. We're actually got lots of SD RAM on this board, so we chose to stick the buffer in there. And yeah, that's how we set it up.
Good, thanks, Gary. Johan, we have a couple questions for about Tracealyzer and Percepio. So the first one is, does Percepio support to MQX? I assume that's for Tracealyzer.
MQX. Not yet. We are, however, working on an SDK that will allow for integrating Tracealyzer with various operating systems. But MQX is not one of those we have predefined support for. The ones we do support at the moment is, well, FreeRTOS in this case, SafeRTOS, MicroC OS3, ThreadX, which is now Azure RTOS, VxWorks. We have a new version for Linux systems coming out soon. We have a beta release next week. There are probably a few more, but not yet MQX.
All right. Another question regarding Tracealyzer. The Tracealyzer demo used a breakpoint and snapshot mode, but is it possible to capture real-time traces from a live running system instead?
Yes, we have what we call streaming mode, where the data is transferred continuously. And this can be used over serial wire output, like in this case, or with a Segger J-Link probe, for instance. And with this, we can capture basically unlimited amount of trace data, as much as you can store on your hard drive on your desktop computer. We have done recordings of 70 hours or so, and we've also ensured that Tracealyzer is able to work with that kind of data. I noticed in Gary's example that his 400 kilobytes trace buffer was a bit slow to open, but that's because the snapshot mode was used, and that is memory optimized, so it's quite compressed. So that's 400 kilobytes is on the large side for a snapshot. Typically, it's more intended for traces of well, down to a few kilobytes. And that also allows it to be used in deployed systems with the dev alert service.
Okay, and then a few more questions for you, Johan. What kind of metrics can you analyze with Tracealyzer?
Well, there are a couple of kind of predefined metrics related to task scheduling, like execution time of tasks, response times, periodicity, things like that. You can get a statistics report, or you can see them plotted over a timeline to see the variations. But you can also insert your own, what we call user events that Crank used in this example, the yellow labels. And then you can, based on those custom points in the trace, you can set up your own metrics by defining what we call custom intervals. And then you get kind of a data set for each of these 2 points and can measure any duration in the trace in a systematic way and see the minimum and maximum durations, etc. So that gives you a much more kind of system-specific and more relevant metric that's more kind of user-defined.
Mm-hmm. Okay, and one more regarding the dev alert service. Can it also handle severe errors like hard faults?
Yes, that's a good question, because I mean, what dev alert does is that it allows you to report an issue to our dev alert service with a trace, but that requires that you upload a few kilobytes of data. And if you have a hard problem that the system basically crashes, then you might not be able to do an upload. You might be in a weird error state. The operating system might not be running anymore. So that's a good question. But what we have done to handle that is that we have a built-in solution to save the data to Flash. The alert is typically a few kilobytes of data, so we have a reserved Flash area where we can write that down. It takes a few milliseconds. And then you can restart the device. And once the system is back online again, the dev alert agent that is included in the firmware will find this data in the Flash and upload it automatically to the dev alert service.
All right, thank you, Johan. Now we have a few questions for Gary and Scott at Crank. So let's start with the first one. What is the CPU load when using Storyboard?
I'll take that, Scott. So it really does depend on what you're doing. So what's interesting with Storyboard is that we're entirely event driven. So when we're not processing some timer or scheduled based event, when we're not moving an animation or doing something on the screen or even processing a touch input, we're using 0 CPU. So we're actually blocked and halted waiting for the next event to arrive. So the complexity in a CPU loading could be obviously 0 and all the way up to pretty much 100% if we're running full screen animations. But it's very bursty, and it does actually depend on the complexity of the application as well. So there's no real answer. You can see the kind of insight that Tracealyzer gives you, and you can measure this dynamically. So it's a very dynamic value. But we work very hard to keep it low and to be optimized where possible using hardware offload such as the PXP chip.
Okay, thanks, Gary. One more for Storyboard. Has there been any effort or is there any plan to make Storyboard qualified for DO 178 use?
Did you want to take that, Scott?
I'll let you take that one because that's
okay.
That's new to me. I haven't heard that one. So DO 178.
So as far as I'm aware, I'm no expert on the certification side of things. This is a military standard, and it's not something that we typically do directly. We do work for automotive, medical, and other safety critical applications. We work with customers to help them certify their own applications. So we're pretty much part of the wider system. So we don't certify in our own right, but we provide the necessary information, traceability, testing strategies, and such that feed into the customer themselves doing the qualification to whichever standard applies. So I hope that's kind of answered your question, but we don't support the DO standard directly, no.
All right, thanks, Gary. All right, we have time for 2 more questions, so we'll round out with this one. How are user events connected to UI actions or changes in the display, especially using C or C++?
Okay, that's cool. So as I mentioned earlier, there's an event-based mechanism, which Scott mentioned earlier on in the slide. We really do try and decouple the user interface from the back-end code, so whatever the machine or the state machine is doing. And the way we do that is using an event queue in each direction. We call them channels. So we have a set of APIs that you can call from C or C++ in the RTOS world, for example. And on maybe a Linux platform, Linux is using separate tasks. So we have a Storyboard engine task and maybe a backend task. So on Linux, it's a system v message queue, and on FreeRTOS, it's a FreeRTOS queue, FreeRTOS message queue. And so you're injecting messages asynchronously into a queue, and the Storyboard engine picks those up and processes them on demand. So as we're event driven, we're not doing anything until those arrive. And then when we do, we can trigger actions and behaviors in the UI based on those event triggers. And we can run custom scripts in Lua or just change data values. So it's very well defined. It's actually quite a simple API. I believe there are quite a few examples on our website if you want to take a look. And we can certainly share some more information regarding knowledge-based articles which explain it in more detail.
Hello, I'm sorry, I'm experiencing difficulty on my end. Can you hear me, Gary?
We can hear you fine, Megan.
Okay,
Yeah.
Sorry.
You mentioned there was maybe a couple more questions, or just about on time.
There's one more, and then we'll go ahead and close out today. So another one for you, Gary. How many megabytes of RAM would be recommended for GUI with Crank Storyboard? How much does the washing machine demo use?
Okay, so when you saw in the UI, it's kind of hard to flip back and show you, but we were predicting the user interface in the designer something like 9 megabytes. That was by virtue of all of these large images we're queuing for the animation. So the real answer is it depends. It depends on a number of factors, the complexity and the number of images, the level of caching that we're enabling, and also, in raw terms, the size of the display, the screen itself. So we require 1 or 2 frame buffers, and those will be at a minimum of RGB 565, so 16-bit, and it depends on the number of pixels on the display. So, it's the number of X pixels times Y pixels times the color depth. And it's quite a complicated answer, but we do have customers in production running on devices with the RT1064, for example, and that has 1 megabyte of onboard flash, 4 megs of onboard flash, and 1 meg of onboard SRAM, and they're successfully running in on I think is a 320 by 240 size display on internal resources only. So it can be done, but it just depends on the complexity of your user interface and the number of images and fonts that are being used. So it's not an exact answer, but I hope that helps.
Thanks, Gary. All right, with that, we'll go ahead and close today's call. I want to thank all of our panelists for their time today, and I want to especially thank all of you for joining this webinar today. Hope you have a nice day.